Right. Let me have a look here. Circular motion. So all the work that we've been looking at so far in terms of the motion that we've been doing, forces we've been applying, momentum that's been looking at been applied to. We won't be looking at momentum applied to this, but we certainly will be starting to look at, now we're starting to move into new territory away from the old physical sciences days, where everything went in a nice straight line. And we're going to look at what makes objects rotate around in a circle. So for instance, to a greater or lesser degree, planets going around the circle of the solar system. What else we got? If any of you have been up to Movie World, been through some of the roller coasters up there, then good luck to you. Doing that, it's quite good fun. Such as that, going around in circles, making yourself feel a bit ill. Spirals and such. Or indeed, if you just like drifting along, going for it, ripping into it and going through from there. The idea of going around a corner is a good thing to be able to do. There are occasions when you can do that. So, the idea of being able to go around a corner, what's actually going on there? Again, the School of Physics, very expensive prop departments, they give you a tennis ball. And if I were to just hurl that across the room, especially in an environment in which there was no gravity at all, and once this ball left my hand, then it would undergo, its motion would be dictated by Newton's first law, which states what's Tom? What do you reckon?
An object will stay at rest at a constant speed as balance force has come.
Exactly. If this is leaving my hand, and okay, if I was in space and threw this out, then what would go? It would go at constant velocity, same speed, same direction, unless an external unbalanced force was acting upon it. Go in a nice straight line. That's how things work. Projectile motion works because once it leaves my hand, there is a force acting upon it, and that force is acting down and it's bringing it back down to the ground. The horizontal velocity is unchanged. The vertical velocity is going through there, in that direction. A little bit of physical science there for you. We've been looking at fancy things. We do parabolas. So we throw it up in the air, goes up, comes back down again. Now, what has causing an object to fall into a circle? Glad you asked. So here we have circular motion. The idea of the whole Earth is spinning around so that you get these nice photographs of the stars, and you can see the circles, the stars going around the circles from there. So, what this means is, if I were to throw this in this direction, and again, very expensive piece of equipment. If I was to throw this in this direction, okay, it would go straight until such time as a force is applied by the piece of string. Okay. Now, if I have this going, so it's coming altitude in that regard, if the velocity is in that direction, but the force is at right angles in that direction, then what's going to happen is that there is an unbalanced force moving in that direction, and it's going to keep the ball's velocity is going to be altered, so it's actually going around the corner. And once the ball is in that position, the force which is pulling it into the centre, okay, is going to keep going round, so that you get. I'm very conscious of the fact that I have actually smacked that projector several times in the past. We'll just go like that. Now, the ball is travelling at constant speed. Okay, 1001, 1002, 1003, 1004. But it is not travelling at a constant velocity. How do we know, Oliver, that it's not travelling at a constant velocity?
Because it's changing direction.
Exactly. Constantly changing direction. So rather than going from that direction, it's now going in that direction, round to that direction, round to that direction, round and round and round and round and round. And if an object is changing direction, Okay, then it must be changing velocity, because the velocity is measured in both magnitude and direction. And if an object is changing, constantly changing velocity, what is it doing? Accelerate. So what that means is that as I swirl this ball over my head, that even though it is travelling at a constant speed, it is undergoing an unbalanced force causing it to constantly accelerate. Which is not something you're going to get with a ball that's travelling in a straight line. Let's have a look at that. So, the component of force acting on a body in a curvilinear motion, in other words, going around a circle, and this is the centre here, don't worry about this bloke standing over here, directed towards the centre of curvature of axis of rotation, the centripetal force, this force that's actually bringing this is the force that is causing the ball to go around in the circle, the centripetal force, is necessary for an object to move with circular motion. So as it comes along here, if that force were not here, then this ball would just spray off at a tangent, which many of you would have done if you've had some sort of catapult as a kid, whirl around your head, get it faster and faster, and then throw it, woo, away it goes. So you release that force from your hand, and it will continue on this direction. And it's going to continue on around that circle. Now, what does that centripetal force look like? So when the ball is whirled in a circle, it is accelerating inward. The ball is accelerating towards the centre. This inward acceleration is caused by a centripetal or centre-seeking force supplied by the tension of the string. Okay? The required force is equal to mv squared on r, and we'll have a look at that in a sec. So the mass times the square of the velocity divided by the radius is going to give you the force that's going there. And the required force, and r is this distance from the centre of the revolution. Now, if this case, if there's a reaction, if there's a centripetal force pulling the ball in this direction, then there's going to be an equal and opposite reaction force on the hand pulling in that direction. Okay. So, if you have your loop-the-loop, what's happening here is that the train is going up over the top. There is a centripetal force pushing into the centre. There's a force that is pulling this train in towards the centre of the loop. And we see this sort of thing in centrifuges, and the size of a centrifuge can vary from your little handheld model, okay, up to the electrical one that you might use in chemistry, okay, up to the monster one that you might get to have a go on if you want to be an airline pilot or an air fighter pilot or an astronaut, such as that. So, many of you may be to the show. You may have risked your life in the hands of, somebody who decides to live in a caravan and travel around the world, travel around Australia, outback Australia for their livelihood, and then put together a gravitron with what can be described as a rusty spanner. Let's see how you go with these things. So, what's happening here is it's spinning up here, and there's going to be the edge of the gravitron. The structure of the gravitron is such that the edge of the, in order to get that going in a circle, that needs to be accelerated into the centre. And what we have here is people having fun going around the outside. Now you might say, ha ha ha. Ha ha ha, Ben. But what's this force that's dragging me towards the centre? How come when I go on the gravitron and I sit up against the wall and I'm being sprayed up here, and when I vomit it just goes all over me and I've got candy floss and Dagwood dog everywhere? What is that all about? Why am I being sprayed up against the outside? Clearly that is this centrifugal force that I know so much about. Okay? No. No. What that is, okay? If you have the gravitron that looks a little like this, point on the outside of the gravitron. If that piece of steel or whatever it is, okay, you've got that moving in that direction. If there was not a force acting on it, then it would go in this direction. But there is not. The structure of the steel, the tension in that, causes this to go around the corner, and so there's going to be a force acting upon that. If you are up against the gravitron here, and this is moving at a velocity in that direction, and the force is pulling on you, then there is going to be an unbalanced force pulling in towards the centre. And if you're up against that, what this means is you would like to be going to go in that direction as well, but you cannot because you've been held up against the gravitron. So this is also the body, the force is being pulled into you in this regard. Now you can feel yourself being pushed against that because that is the equal and opposite force. So the gravitron is pulling against you towards the centre, and you are pushing against it as a gravitron. The equal opposite force in that direction. Now you can get caught up in this centrifugal debate, or centrifugal if you prefer. I prefer to call it centrifugal because it makes it sound a bit sillier. Debate, but it all depends on your position. If you're standing outside as an external observer, then you can see what's happening here. If you are sitting here and spinning around with this, and all you're seeing is an unbalanced force pushing against that, then you might argue that there is this centrifugal force, but I would disagree with that. Alright, pilot training, it's always good fun. Let's do this. See how these guys get on. Now, you can turn it off for a second. You like the ice?
You bought a Jeep.
Yeah, I bought a Jeep.
We're going to need a bigger boat.
Alright, your first ride is going to be that gradual onset ride to a maximum of 7 Gs.
So what we see here is the G rating up here.
Yeah, right.
So the thing in there, and what's that go up?
Are you ready?
Yes, sir. I'm ready.
Okay. 3, 2, 1, engage. How you doing?
If you lose all the green,
3
coming
G's
down,
in.
start that lower body straight, okay?
Okay.
Squeeze those legs nice and tight. 1, 2, breathe. You're looking real good. Squeeze everything nice and tight.
I'm moving it.
Not yet. It's only 2 G's.
Okay.
It's only 2 G's.
Feel like you're going straight up in the air at this point?
Awesome.
That's 4 G right there. You're doing good.
3, 2, 1, engage. Back on the stick.
1, 2, 3,
On top.
5 G's.
On top, breathe. You're on top, breathe. You're on top, breathe.
I'm moving it. Okay, big breath. Walk out the road.
You're on top, breathe. Hold. On top, breathe. 1, 2, breathe.
1, 2, 3. No shield breath.
1, 2, breathe. 1, 2, breathe. 1, 2, breathe.
Okay?
No.
Legs tight. Foot tight. Breathe.
1, 2, 3.
1, 2. Okay. Stay tight. Stay tight. Stay tight. Stay tight. Hello? Are you with me? Coming back around? Hello? How you doing?
What?
Hello, Will?
Hello.
Will, sit up.
I'm up.
Sit up.
I'm up.
You're up. Put your head up.
It is up.
Put your head up.
Oh.
Do you know what happened?
Yeah.
you a lock.
Yeah.
Happened.
I'm taking out a key-lock.
All right.
Okay, you ready? You feeling nauseated?
Yeah, a little bit. I'm gonna vomit.
Okay, get the bag. Get the bag.
It was a bitter day.
I actually have no comment for you. Everything looked real good. How you feel?
Woo!
Good job.
Sorry, it's good there. Stick that back on there. Is it still going? Or are you still? So I'll put that, if you're watching out the video, I'll put that up on the front side so you can have a look at that. So how do we know, in a slightly more formal sense, how does this actually look in terms of the circular motion? Well, let's consider the change in velocity that's going on here. So, if we had, for instance, if we go around the circle, let's consider point A is at point 1, and then quarter of a turn later, point B, the velocity or the vector for the movement at that point is going to be, the instantaneous velocity is going to be at that point. So, we know that it's going to be a right angle. It's just going to be the tangential instantaneous velocity of that one is going to be at right angle in both those cases. So if that's going to be the case, what we want to have a look at is what is the change in velocity at that point. And the change in velocity is going to be the final velocity minus the initial velocity. So you can have a look at that. In other words, V2 subtract V1 in that. Now we go back to have a think about difference of vectors. Okay, we don't actually subtract vectors. What we do is we take the second vector and we invert that and add them together. So what we get here is you've got the V2 in this case, and we added that one into that one. And when we add those two together to get the result vector, V1, what happens magically is that forms, those vectors are the same magnitude, so it gives a nice 45-degree, and it's pointing straight back down at the centre. So that change in velocity is pointing towards the centre. So you can see that. So that's how the equation of circular motion. So if we have this circle, and we have this motion with a velocity v, and we have a distance r, okay, then the acceleration that's being felt by this vector is such that the centripetal acceleration is equal to v squared divided by r. So, if I want that acceleration to be greater, I can do two things. I can either make it go faster, okay, so what's happening here is the string is pulling harder on the ball, which in turn is pulling back on my finger, and I can feel that pulling against my finger quite hard. We'll do a practice to check this out next week. Or the alternative is to do the same speed, so I'll go 1, 2, 3. But if I reduce the radius, then the acceleration is going to be increasing. And since F is equal to ma, due to Newton's second law, we can work out what the centripetal force is going to be, simply by mv squared on r, and we saw that in the previous slide. Now, in order to find out the area. We've got R around the outside, okay? Now the velocity here, the instantaneous velocity, okay, is going to be the total distance that it goes divided by the time. So V is equal to S on T. I'll do little t to start off with. Now, what we have there is the distance around the outside. If you know the radius, the circumference is going to be equal to pi times d, or 2 pi r. 2 times pi times r, and divide that by t, where t is equal to the period in seconds. So how long it takes to do one revolution, period, it's going to be long. So we have the velocity is equal to 2 times pi times r divided by t, and we have the centripetal force is equal to m times v squared on r. When you combine those two, substituting for the value of v, we get a equation for centripetal acceleration and for centripetal force, such that m times 4 times pi squared on r on t squared. And that is on your information sheet. On the first page, so we've got centripetal acceleration equals v squared on r, which equals 4 times pi squared r on t squared, which is on your information sheet. And similarly, we have centripetal force equal to mv squared on r, which equals m4 pi squared r on t squared. And those formula are on your information sheet. Okay. So that's a crack. Why is there no apostrophe on it? Very poor form. So, a motorcycle and a rider with a mass of 1,250 kilograms. Sounds a bit like Ollie, is that right?
Yeah.
Must be a big bike, mate. What have you got there? Are travelling around a circular track on a radius 50 metres at a constant speed of 40 metres per second. So we're going to calculate the centripetal acceleration, the centripetal force, and the time it takes to complete one. Should be reasonably straightforward. So, we know the constant speed and we know the radius. So getting the centripetal acceleration is going to be pretty straightforward. 40 squared on 50, and we end up with 32 metres per second squared. In which direction? Towards the centre of the circle. Bear that in mind. Part B. Simply a matter of multiplying through by m, so that the force, the unbalanced force going through is going to be 40,000 newtons towards the centre of the circle. And finally, what's the period going to be? Well, we know the velocity is equal to 2 times pi times r on t. So rearrange that and we get that. And it's going to take 7.85 seconds to go around the circle. The maths itself is reasonably straightforward. The point that I want you to get across is the fact that an object going around a circle is, suffering for a better word, is undergoing an unbalanced force. Even though the speed is constant, that there is an unbalanced, net unbalanced force acting on that object going around a circle. If you understand that, then you'll understand pretty much everything. Oh.
So the circular track, does that mean like this, and it's riding literally horizontal inside the circle?
So circular track, just a flat track.
So like on the ground.
On the ground, looking down on the top. Going down there. Now the reason they bank tracks, and we'll have a look at this shortly, okay, is that you see this is bank tracks as you're going around corners. Okay. And we'll we'll have a look at how that helps with the idea of this, and why tracks that can be the wrong way are particularly dangerous. Okay, now I have got some questions. Set 15. Chapter should be chapter 15. I should. No, garden. Sorry, garden. These are the garden questions. One, 6, 8, and 10. Anything on the next page? And new century. And it should be one more. So I'll hand out. I've got some circular motion sheet questions. There's all sorts of questions there. So the sheet that I've got here for you with circular motion questions on it. There are new century questions to do on chapter 5, or there's Gardner questions as well. There's a whole myriad of those.